everybody. So my final proof, which is so exciting that it's the last one, is going to be on the fundamental theorem of calculus, both part 1 and 2. So my name is Alexis, and my co-provers are Jacqueline Beck, Sandra Torres, and then Ziying Pen. And then uh, let's just get right into it. We have our equations right here. And first things first, we have some definitions or things to keep in mind, and then we're also going to state the theorems at the very end of this section. So the first thing to keep in mind is when something is continuous. So when a function is continuous, it means there are no holes or jumps. It's just fluid throughout the entire thing. And another definition that we need to keep in mind is differentiability. So you can pick a point within the function, and the derivative for that point will also exist. We also need to keep in mind open and closed intervals. So given a specific range, an open interval does not include the endpoints, and it's listed in the form AB with parentheses. A closed interval, on the other hand, you must include the endpoints, and it includes a hard bracket for AB. The other thing that we need to keep in mind is derivatives. This refers to the rate of change of a function, and it'll appear as d divided by dx. And its formal definition is the limit as h goes to 0 is f of x plus h minus f of x over h, which we'll be using for our proof. Another thing to keep in mind is the antiderivative. So this is the inverse of our derivative and also called an integral. It will appear as the integral f of x dx is equal to big F of x plus c. And this is a little bit of what we will be proving. So going into it, we have our fundamental theorem of calculus, the first part. This theorem states that if f is continuous on a function on a closed interval AB, then the integral of the function g defined by g of x is equal to the integral from a to x f of t dt is continuous on a closed interval AB and differentiable on a open interval AB, and g prime of x is also equal to f of x. Our second theorem states that if f is continuous on a closed interval AB and f prime of x is equal to f of x, which is part of our first theorem, then our integral from a to b of f of x dx is equal to big F of b minus big F of a. Okay, so first we are going to be doing some examples proving or showing how each of them really work. So we have two functions. So let a of x be equal to the integral from 4 to x cosine of t dt, and then let b of x equal to the integral from 4 to 6 t to the fourth power dt. So we need to solve for a prime of x and then b of x using FTC1 and FTC2. So we know that our f of x is equal to cosine of x and the lower integral of a is equal to 4. So if we were to take the derivative of our integral, it would appear as follows. So we have our derivative right here, and then the integral as is. If we were to solve for the integral first, we'd be left with sine of x. It should be, and we have a constant, which would be our negative sine of 4. However, when we take the derivative of the function, because sine of 4 is a constant, it will just go straight to 0, leaving the derivative of just sine of x, which is again cosine of x. And we can simplify that by stating that the derivative of the integral 4 to x cosine of dt is equal to f of x, which is equal to cosine of x. Therefore, a prime of x is equal to f of x, which is equal to cosine of x. Okay, now for our second example, we have given b of x is equal to the integral from 4 to 6, and then it's t to the fourth power dt. We have our function, and there's a typo right there, but we have our function right here. And when we take the antiderivative, we are left with t to the fifth power over 5 from the bounds 4 to 6. And then when we start simplifying everything and plugging everything in, we have 6 to the 5th power divided by 5 minus 4 to the 5th power divided by 5. That's 7,776 divided by 5 minus 1,024 divided by 5, which gives us 1,555.2 minus 204.8, which finally evaluates to 1350.4. Okay, so now we're going to be going into our proofs, and we're going to start with part 1, obviously, because we need part 1 in order to prove part 2. So let's just assume that we have a cumulative area function that we'll define as a of x, where it is defined as a of x is the integral from a to x f of t dt. So the way that integrals work is we're trying to find the area underneath the curve, and this is the function that is going to give us our answer. Now, note that we need to show that a prime of x is equal to f of x. And for integrals, like I stated, we're trying to find the area under the curve. And typically how we do that is we use a trapezoid function. I can show you a little bit of the graph over here where it's a trapezoidal area where they break it up into sections and use that. And the area would be equal to 1/2 b1 plus b2 times h. So when we recall that we need to apply the derivative to a of x because we are trying to show that a prime of x is equal to f of x. And by definition of our integral, because we stated it above right here, when we plug in our derivative for a of x, we get, let me scroll down, the limit as h goes to 0, and it is a of x plus h minus a of x over h. Since we have previously defined our a of x, which is right here at the beginning, we can substitute this in for our limit function. And so we have the integral as the limit goes to, for h goes to 0, we have the integral from a to x plus h f of t dt minus a to x f of t dt all over h. And because of our lower limit, we can combine the two integrals because we need to be able to evaluate a smaller like trapezoidal area, which is the graph shown below that I showed earlier, and we can combine them right here. And let's just go a little bit more in depth into what that means. So the area, we have the area under the curve, but because we're evaluating this more specifically, we're looking at this trapezoidal area right here. And because of this, we can see right here, our a x plus h minus a of x is also equal to f of x plus h times h, I mean. And we're evaluating this little area right there, which is why we're able to do this and combine the two. And since I previously stated, a of x plus h minus a of x is equal to approximately f of x times h, because our h is right here, as you can tell, because obviously from x to x plus h, the difference in this length is h. So when we're evaluated, we're left with this, and when we plug that into the equation, we get the limit as h goes to 0 is h times f of x over h, and because there is an h on both sides in the numerator and denominator, we can just cancel that, so it leaves the limit going as h approaches 0 is f of x. However, recall that since our limit is only evaluating when h goes to 0, our limit is f of x because there are no h's to evaluate that. Therefore, when we have the integral from a to x, our integral of a to x is the antiderivative of f of x, meaning that a prime of x is equal to f of x. Okay, so now we're going to get into our second proof of FTC. We want to determine how to properly measure the area under the curve of the function given a specific interval. So for this proof, we need to consider a general function f of x. So we have it right here. It does say a big f of x, but this should be an a. Okay, but recall, in order to do this manually, we would have to break each little section into small pieces and calculate the trapezoidal area over and over, which would take so long to approximate for a specific interval like this. So we're going to be using our integral from the previous proof. So suppose we have the same function defined as a of x is equal to the integral from a to x f of t dt. So by FTC1, we already know because we proved it that a prime of x is equal to f prime of x, which is f of x. However, when evaluating indefinite integrals, we know that they can leave behind a constant c such that a of x minus f of x is equal to c. Therefore, there exists a constant such that a of x is equal to f of x plus c, and we can get this by manipulating this equation right here by moving it the f of x to the other side. So in order to evaluate our constant, we need to plug in the lower integral when x equals a, so it would appear as such. So a of a is equal to the integral from a to a f of t dt. And notice, since the upper and lower integrals are the same, because it's a to a, that means that there is technically no area to evaluate, which means, oh, this is supposed to say a of a is equal to 0. Therefore, when we plug in this, it is equal to 0, which is equal to f of a plus c. I can show this a little bit. Like, let's suppose that we're taking the integral from a to a, it would just be right here. There is no area that we can calculate, since technically this is all going back to evaluating the area under the curve. Okay, now we need to evaluate our upper integral, which we would say, because of the interval we're given, we would say is a of b, which would be equal to big F of b plus c. And also we recall that since we're plugging in x equals b, it will also appear like this. The integral from a to b f of t dt is equal to f of b plus c. Okay, yeah, now recall in our graph that we mentioned finding the area, and in order to find the area that we normally would using this function, we would just subtract each interval to find the area between them, so we can infer that a of b minus a of a would give us that area. And because we already determined what these functions looked like, when they're expanded, we can substitute everything into the function, and now it'll start to look a little bit familiar. So we have a of b minus a of a is equal to f of b plus c, which we get right from right here, and is equal to f of a minus, plus c, which we get right here. And then we can also plug in our values for a of b and a of a. So we get this integral function from up here when we defined it earlier, and we also get 0 because we stated that the area from a to a is 0. And finally, we can remove the parentheses and start simplifying things that are the same. So therefore, we have our constants canceling out, which leaves us with the integral from a to b f of t dt is equal to big f of b minus big F of a. Therefore, when evaluating the area under the curve on the interval ab, the antiderivative is f of b minus f of a. And that concludes the proof. The second one is a little bit easier to understand, but I hope you guys really enjoyed, and I hope you guys have a really good summer. and enjoy your vacation. Hopefully all of your proofs go well and hopefully you have a good time on the homework as well. So I will see you guys in class, I guess. Have a good day.